Hello, in this video we're going to have an introductory look at some forms of tactical and strategic AI, including board game AI. If we're thinking about tactical and strategic AI in terms of how it fits into the grand scheme of things, so this is higher level forms of artificial intelligence. It quite often assumes that there is basic, for example, steering behaviors or decision-making behaviors at an individual level. When we get up looking at strategic and tactical AI, we're thinking longer term. We may be trying to plan over a longer period of time to take into account, if you like, sizable goals, or we may be trying to coordinate the behavior of a number of different objects so they all act in some coordinated, coherent way with a single purpose or goal in mind. The forms of tactical and strategic AI that we'll look at, this is a large area, and you can see here that, basically in terms of defining is what we've mentioned is by driving a tactical assessment or making decisions or coordinating multiple characters. We very much are only going to scratch the surface of this, so we'll look at a few example mechanisms whereby we can get in some tactical or strategic information, and to give you a few illustrations of how it is used. Not all games need to have this level of artificial intelligence, and at this level invariably it tends to be restricted to the particular nature of the game that's been played. This is just very much a flavouring of some forms of tactical and strategic behaviour. We'll start off having a look at one quite common way that you can encode higher level forms of information into, for example, a map. Waypoints are one of the ways in which that can be done. And when we were thinking about pathfinding, we really had a look at a waypoint graph, which was one of the mechanisms we could use to actually define a walkable region or points that characters can walk between. By taking that basic idea of having a waypoint, and this notion broadly extends to grids-based approach as well, we can add an additional information to those waypoints or those grids. So types of information we might add in could include, for example, cover points. So if we're looking at the diagram, we're assuming this is, say, a top-down view of maybe an office with some sort of plants and chairs and tables. We could identify cover points as those which are behind something that provides cover. We could provide reconnaissance points, ones with sort of good line of sight. Shadowed locations if you want to have a character that tries to remain hidden. Power-up spawn points if you have those, exposed locations or other things, and so on. Quite often it would be the designer that would actually put these different points in, though actually you can also build them algorithmically too, by analysing the environment, or actually by looking at a lot of how players have played within the map and then deriving information for different regions based on those styles of play. But that's one way that we can augment or basic, if you like, navigation mesh, the thing that we can walk through, to include information that's slightly more higher level, more tactical, can be more strategic. Having done that, what it means then is that we can, for example, extend our pathfinding so that it uses this additional information, so that it naturally weights it higher in certain ways. So if you wanted a character that moved cautiously, then any cover point that was exposed, you would give it a much higher movement cost. And anything that was uncovered, you would give it a low movement cost. That means the character would be inclined to keep the cover as they move through. Same notion applies, for example, to light, to darkness, to shadow as well. So by adding in that additional information, it enables us then to tweak things like, for example, pathfinding, and to give us then tactically aware pathfinding. Almost comes out of it fairly easily. Another quite common challenge that's faced, particularly at a strategic level, is, well, how do you work out where the front is? Where do you expand? Where there's points of contention between different players? One of the most common ways of doing that is actually using what's known as an influence map. And this defines out the regions of the map that are under the control of each of the different players. So we'll have a look at how a very simple influence map could be created. Quite often they're sort of grid-based, or at least they chop the world up into grid-based size chunks. And each chunk then we're going to say that the different players may extend influence over it. And depending on who's the most influence in that particular tile, they'll be the ones that will end up, if you like, notionally owning that particular tile. And by using an influence map, we can use it for driving, if you like, where the front line is, where particular areas of strength are, either for the AI or for the opponent, where areas which are uncontested are that are potentially good for expanding into. So let's have an example of this. And we're going to have, you can see sort of a map over here where it's tile-based. We've got sort of a green grassy land, we've got notionally a blue sort of river, we've got sort of a dark grey, let's say mountainous range. And we've got a few different units. I've got a couple of, on the right hand side of our map, we've got a sort of a black unit and a black city, and a white city over on the left hand side. And we could assume that the different units or entities, the bases, they emit influence. It extends out from them, but it decays over distance. And that for some of the terrain, influence passes, a lot more difficult in other bits. So let's take, for example, the unit we see down at the bottom. And let's say that it is an influence value of 3. And it decays then by 1 across each tile that it moves out. So you can see there then that we have a decay in the influence. We could, for example, say that the influence decays quicker over water. So there that the unit, his influence extends a little bit onto the water, but not beyond the water. We could also, for example, say for the base, it is a stronger influence, a value of 5, and again we get that decaying. And if you look at the 5, 4, 3, 2, 1 going straight down from the base, you see then that we have in regions where the influence of the base and the unit overlap. And there we actually add up their net influence. We're saying our mountain range, it sort of blocks influence as well, so that the base doesn't extend much beyond that. We can also do exactly the same for the white base and give its influence scores. And so again, it's extending, it's dropping quicker over water, but we have our bridge and that lets the influence then pass through. Now, it's reasonably quick to actually calculate these different values and to update these different values. Once we've done that, by having a look at the different squares, we can do lots of interesting things. So, for example, the areas that only have white influence, we can say that this is uncontested area that simply belongs to the white player. And areas that have black influence are uncontested, simply belong to the black player. And then we have a region, well, two regions really. We've one area where we have a mixture of influences from the two sides, and we have a third area up in the top left-hand corner where there's no influence, so that's a good area for expanding into. Those areas where we have white having a stronger influence than the black player, then we can sort of say, okay, balance of this is contested square, but balance belongs to the white side. Likewise with the other one, we'll say balance belongs into the black side. And areas where it is of equal influence, we can sort of say these are the front line. It's truly contested there, that there's no one owner. And having done that, then that gives us, if you like, useful information that we can use, for example, directing characters if they want to get to the front line or things like that. Having looked at a couple of introductory forms of strategic and tactical behaviour, let's also have a quick look at board game AI in terms of how artificial intelligence work when they're trying to play board games against a player. Board games, that there's actually a long history in artificial intelligence of getting computers to play them. In fact, it was some of the very, very first applications of artificial intelligence, playing things like chess or checkers. There's lots of different types of board games, and we're going to define some of their characteristics. But for most of these algorithms, it sort of assumes it's a two-player game. You've got the player and you've got the computer, but you can extend that out to more than one player if you want to. And again, depending on the game, most games have the notion of a player takes his or her turn, and sort of some sort of round-robin approach then by way of cycling around the players. By way of adding a little bit of terminology into this, there is the notion of what's known as a zero-sum game. This is a board game in which if a player wins, then the other player loses. So it's zero-sum. If one player wins, the other player loses. So for example, chess is an example where there's a winner and a loser. It's zero-sum because overall, you've got a winner and a loser, kind of averages out. For some casino games, that's not the case. In that case, you're sort of playing against the house, and each player is sort of somewhat independent. So everybody then can be winners, or more likely everybody's going to be losers, other than the house. The interesting thing about a zero-sum game, and this is, I suppose, key to the artificial intelligence around this here. There's two ways you can approach an AI playing a zero-sum game. You can either focus on trying to get the player to win, or you can focus on making the opponent lose. Now, these are flip sides of exactly the same coin. If you focus on getting the player to win, then if they win, they've won and the other player loses. If you focus on getting the opponent to lose, then because it's zero-sum, it means the player, on the other hand, will win. And so the outcome's exactly the same. And that important distinction about sort of viewing it from making the player win and making the opponent lose is going to come into one of the key algorithms that is known as a minimaxing algorithm. For other games which don't simply include just two players and zero-sum, it does or it can get a lot more complex. You know, that if you have multiple players, then you get into the whole notion of having temporary alliances. So you know, what we're looking at here is very much sort of introductory AI in terms of board games. Other characteristic to take into mind for these types of games is the information. You can either have a perfect or imperfect information. So perfect information is, as the name suggests, you know everything about the game state. So for example, in chess, you can look at the board, you can see the location of every single piece on it is perfect information. If you think of the game, for example, of battleships, there you have imperfect information, and the whole premise of that game is actually to have some strategy or technique of working out where they are. And some games have a mixture. I mean, your traditional classical real-time strategy game, you have a sort of a fog of war where there's some areas you're visible to and some areas that you're not visible to. If you involve dice or a die being thrown, then again, because there's a random outcome, you may be able to predict things within certain boundaries, but you can't predict the exact outcome, so again, that's an imperfect information or imperfect game. What we will be assuming here, and we're going to look at an algorithm that works for two-player, perfect information, zero-sum games. So this is one particular type of board game that we are interested in, also happens to be the most common, but specifically that's what we're looking at. For other different types of board games, you need different algorithms. In developing the algorithm, we're going to have a look at what's known as the game tree. Now, the game tree really applies very broadly to board games. It's not specifically our two-player perfect information zero-sum. It does apply more broadly as well. Game tree is one of the key underlying data structures. It represents a evolution of the game. So normally at the top of the tree it represents the current state of the board, and as the tree expands down on subsequent levels, you represent how the game might actually evolve. So at the top we have the current state, the next level down, and there can be there's different branching factors here, but at that particular next level down we would show the game one move on. So here we have X's and O's, and at the top we've got X in the center and an O up in the top right. It's X's go, we're assuming here, so the next row we would show all of the different moves that X could make. And then underneath that we show all of the moves that O could make. So we're if you like, etching out how the game can evolve. If we get to a winning condition down at the end of the game, then normally the leaf nodes, if depending how big the tree is, the leaf nodes you get down at the very bottom of the tree, if the player wins then it's +1, if the player loses, the opponent wins, then it's -1, and so you can give, if you like, a score to it. Now you can probably get a feel, I mean, for noughts and crosses, tic-tac-toe, very simple game. If you actually think about this tree, it's a massive tree, and what's known as the branching factor, it depends upon the number of moves you can make at each point in the game, and where the depth of the tree is roughly speaking, the number of moves that it would take to actually complete the game. And for some games, chess or things like that, this tree is gargantuan. It's bigger than you could ever realistically store in memory. So you have to get into a search algorithm that tries to more efficiently go through the space. But as a concept, the game tree is quite a useful concept. So given given a particular board position, we want to write a piece of AI that decides what is the next move or the next plausible move. Now at any particular point this is going to be something that is very much dependent upon the game. And you can see in the aside here that, for example, for reverse E and for chess, you can read it, that there's different strategies that kick in at different phases and stages within the game. So when we're talking about it's known as a heuristic or evaluation or static evaluations function, it's one you can give it a particular board position and then say, in this particular position, what is the next move that you could make? And quite often these things, you can either pick one move, you could pick all possible moves. They will return a number of what looks to be sensible moves at this particular point. And that's going to be important because the quality with which we pick this particular sensible move at this point in time is going to be one of the factors that will determine how effectively we play, and also how deep we can run our particular decision tree on it. So minimaxing, this is how all of these things then tie together. We have our static evaluation function, we've got our game tree, and we're going to then link them together in what's known as a minimaxing approach. And this is sort of the de facto common or standard algorithm that's used here, or as the base of a lot of the common algorithms. Sort of alphabet pruning is the more common one. How minimaxing works is that when it is the player's move, the algorithm will act to maximize the score of the player. That makes sense. And when it is the opponent's move, because you assume that the opponent, him or herself, is trying to win, the algorithm will act to minimize the score of the player. So it has this maximizing followed by a minimizing step. So basically this algorithm is trying to plan ahead in terms of the player's moves and the opponent's moves, assuming that the opponent is going to try to win and to lower the player's score. So alternates between maximizing, then minimizing, maximizing and then minimizing. And that sort of reflects for two-player the sort of the back and forth nature of the game. So we can have a look at the algorithm for doing this. Let's say we have a method called getBestMove, and it returns a move. And we pass into it, well, what's the board state that we're currently using, and then the player that is going to be taking that particular move. And it's going to be a recursive function, so minimax will be a recursive call, and for the most simple implementation of it, that's what we'll use. When we call minimax, we assume that it will return a couple of useful pieces of information. It's going to return a score, which evaluates, if you like, how promising or how good for the player's point of view that particular move is. Then a move itself that you make from that particular position. Now, ultimately, when we call this, when the player calls this, they're not interested in the score information. They just want to know, well, what's my next move? So we're just returning the next move from it. The other thing, the score will come into the recursive element. So it's going to be a recursive function. Takes in the board state, takes in the player, takes in the maximum depth. So this is how many moves ahead in the future are we willing to look. If we say, for example, max depth is 5, then it's or moves, the opponents, or moves, the opponents, and or moves. So I'll look 5 moves ahead in terms of how far into the future it's going to consider. Also, I mean, obviously, the bigger you pick it, the slower the algorithm runs. So there's a balancing act here. The current depth then is, well, how far down our search tree are we at the minute? So initially when we call our minimax, we pass in a value of 0, so we're at the root node. So the first thing we do is a recursive algorithm. We need to have a condition that gets us out of the recursion. In this case, there's a couple of conditions that gets out of the recursion. If we have reached a game over state, so we've maybe 2 moves into it and it's game over for one of the players, then we should finish our recursion. Alternatively, if the current depth is equal to the maximum depth, we've hit the bottom, again we should get out of it. In that particular case, when the recursion is finished, we're assuming that our board has an evaluate function. We can say for which player, and it will tell us the score then for that player. So +1 if they win, -1 if they lose, and let's assume that we have a ranged value within there. That 0.7 would represent a board state that is favourable to the player. -0.2 would represent a board state that is slightly unfavourable to the player. So you have a value that gives you an indication of just how well the player is doing. Beyond the return from recursion, then we're into the recursive element. And we're going to be trying out different moves to try to find, well, what is the best move for us to take at this point in time? So we're going to remember our current best move and our best score. And there we've got a check here for the current player to say, okay, well, are we trying to minimize or maximize there? Now, the best score, if you have a look at this here, if we are trying to maximize it, so in other words, the current player is equal to the player, then our starting best score should actually be the lowest score possible because we're trying to go up, we're trying to get something bigger. So if the current player on the board is equal to the player, then our best score is equal to minus max score. Lowest possible one because we want to maximize it. If we are in a minimizing approach, so in other words, the current player is the opponent, then the best move is the one that minimizes the score. So we want to try to get the opponent to lose. So in that case, the best score we start off with then is the maximum value we can have because we want to reduce it, we want to lower it down. So think about that there. It takes you maybe a little bit to get around, but this comes into, are we trying to maximize or are we trying to minimize? Is it the current player whose score we're trying to maximize? Is it the opponent whose score we're trying to minimize? Having done that setup, we then assume that we have this is our static evaluation function, get valid moves. We go to board state and we say, okay, based on the current state of the board, what are the valid moves? Now, maybe, well, the method name for this would maybe suggest you'd return all valid moves, and you could, but that would be too expensive. So a good static evaluation function here will only return the promising, a small number of promising, sensible moves. Not the silly moves, not the pointless moves, just the ones that are sensible at this particular position. And that gives us, for this board, our set of moves that we might want to, or which we will consider. We go through those. We create a new board state by making the move that we're considering at this point in time. So we update the board. This is a hypothetical update. And we then recursively work on that. So we're calling a recursive function again. We're passing in our new board state, we're passing in the player, maximum depth, current step, +1. And this will, if you like, if you think then through the recursive bit, we've got one player, we considered one move, we'll keep repeating that process all the way down to the bottom of the recursive search. Whenever this eventually returns, again there'll be a lot of recursion within this depending on your maximum depth, we will have got the particular score of us making that move. So if we make that move and then whatever moves beyond and look at either the maximum depth or the ending depths, is it a good move for the player? Is it not a good move? What type of score do we get out of this here? What's the best score? We check then to see, okay, we've made that. We know what it's going to mean in terms of the score to the player. Then we check to see, well, is this the best move that we've seen out of the set that we've considered so far? And here we have a check to see, okay, are we trying to maximize the player score or minimize the opponent's score? And this determines how we update the best score. At the end of the recursion, once we've gone through this, we simply return out of it with the best score and, more importantly, the best move that we have found. So I mean, it's actually slow as implemented here, and a lot of the implementation is how do you actually get this to run as fast as it can. But at a high level, it's a fairly straightforward implementation. There are lots and lots of different approaches in this, and all basically they come down to more intelligently going through the search space, because search space is massive. So there's a common algorithm known as alpha beta pruning, which is one that will quite quickly prune out areas of the tree that couldn't possibly hold the optimal solution. So if you get a really bad move and there's ways then of sort of saying, okay, well, it can't possibly be better than this move, you can discard that portion of the tree. So that's a way of more efficiently pruning the tree. You can also use things like transposition tables. So again, this is ways of speeding up the recursive element. Or you can use opening books, other standard ways of sort of encoding expert knowledge, again by way of saying of improving your choice of moves at any particular point. So I mean, a lot of things you can potentially put in here to help speed up the process. Key takeaways then, I mean, there's loads and loads of different forms of strategic and tactical AI. We've only touching the surface. One example form of strategic, one example form of tactical, and a bit about board game AI. Obviously, what approach is right if you have a game that requires this? And, it does depend a degree of tailoring and selection based upon the game you have at hand.